You have seen the concept of two coupled masses, and in this regard we have obtained the normal modes of oscillations in case of longitudinal oscillations. And as you know, in this case there are two types of oscillations, that is longitudinal oscillation and transverse oscillations. We have already completed the concept of longitudinal oscillations. So today our aim is to discuss to find the normal modes of transverse oscillations of two coupled masses. Okay, and in this regard you can see this figure. Actually here I have shown that there is a coupled system consisting of three identical springs. You can see this is your first spring, this is your second spring, and this is the third spring, which is actually called coupling spring, because this third spring couples or connects the two masses A and B. Okay. Actually each spring has a relaxed length L0 and the spring constant equal to K. And both the masses are of equal mass, that is we consider that A and B both are equally massive and we take their masses equal to m. Okay. In fact in this figure A I have shown that the springs are actually elongated by same amount in its equilibrium position. So the figure A refers the equilibrium state of our system, in which length of the springs, each spring is equal to L. Although we have considered that L0 is the natural length of the spring, but in equilibrium state the springs are something elongated and their lengths are equal to L. So L minus L0, this is actually the extension or the elongation of each spring in equilibrium state. Okay. And if the elongation of the spring in equilibrium state is L minus L0, can you say what will be the tension developed in each spring in this condition? You can definitely say that the tension T, which will be developed in each spring in this equilibrium state, will be equal to a spring constant K times elongation of the spring, which is L minus L0. So I have shown that in each spring in equilibrium state the tension is T, and this T is equal to K times L minus L0. Okay. Now in the second figure, that is in figure B, I have shown the situation of or you can say the general configuration of the system in transverse oscillations. If your aim is to create a situation so that this system will perform a transverse oscillation, what you have to do? In fact, you have seen that in case of longitudinal oscillation, we have to displace the masses A and B longitudinally, that is along this x-axis. But if our aim is to create the transverse oscillation of the system, we have to disturb or we have to displace the masses A and B in a direction perpendicular to this x-axis. So I have shown in this figure B that mass A has been displaced by psi A in y direction, and mass B has been displaced by psi B also in y direction. And after that the system is released. Actually in this condition you will see that restoring force will act on both the masses, and under that restoring force the system will oscillate in transverse manner. that is, this will oscillate about the equilibrium position which was here and here. So, and this oscillation will take place like this. Okay. So, to find the normal modes of oscillation of this transverse vibration, first of all, we have to write down the equations of motion of the two moving parts of this system. That is the equation of motion of mass A and that of B. And for finding the equation of motion, definitely you will have to find the forces acting on these two masses. As the oscillation takes place under restoring forces, so in this free body diagram, I have shown only the restoring forces. Other forces have not been shown in this figure. So, let us now consider that when the system is disturbed or displaced, as you can see, A is displaced by psi A and B is displaced by psi B in y direction. Then we consider that the length of the spring 1, which was originally L in equilibrium state, now becomes L1. Okay, and the length of spring 2, which was L in case of equilibrium, now becomes L2, and the length of the third spring, which connects the two masses, which was also L in equilibrium state, as you can see in figure A, now becomes L3. Okay, so tensions in these springs will now changed. In equilibrium state, we have considered that T is the tension in each spring, and that T is equal to K times L minus L naught. But now the tensions in the three springs will be different because they will be elongated by different amounts. You can see that what will be the tension in the first spring. If you consider that now the tension in the first spring is T1, then what will be this T1? This will be a spring constant K times its elongation. Since original length, that is natural length or relaxed length of the spring 1 was L0, and now its length is L1. So elongation will be L1 minus L0. And this is the tension developed in the first spring in displaced state, or you can say at any moment T. Okay. Similarly, you can see the tension developed in the second spring. If we assume that it is T2, what will be that? That will be K times L2 minus L0. And the tension developed in the third spring, T3, will be given by K times L3 minus L0. L3 minus L0. Okay. Actually, these forces acting on the masses A and B, I have shown in this figure C in this free body diagram. You can see the tension developed in spring 1, that is T1, will act on A in this direction, as you can see in this figure. Okay, and the tension T3 developed in third spring acts on this A in this direction, as I am showing here. Okay. Similarly, the tension force developed in the spring acting on mass B due to the tension developed in second spring T2 acts in this direction, as you can see. I have marked it by this arrowhead. Okay, and we also experience force T3 in this direction, as you can see, which I am showing here, due to the spring number 3. Okay. Now for calculation, we consider that this angle which the spring 1 makes with the horizontal, that is x-axis, is alpha 1. The angle made by the spring number 2 with x-axis is alpha 2. You can see the figure, and the spring third spring makes an angle alpha 3 with the x-axis. You can see here. Now, resolving the forces acting on each mass, you can find the restoring force. As you know, transverse vibration will take place under the restoring force acting on the masses A and B. And if you displace the mass in upward direction, as you can see in this figure, then restoring force will act at that moment in downward direction, because that restoring force will pull down the masses to its equilibrium position, but due to inertia, the mass will shoot out from the equilibrium position and perform oscillation. Okay, so you have to find what are the forces acting on each mass in downward direction at its displaced position. The net force acting on any mass in downward direction will be the restoring force. Okay, so let us see the free body diagram, and we have to see what will be the forces acting on mass A in downward direction. Okay, actually, for your convenience, what I have explained just now, I have written it here in very detail. So you are advised to note down these things in your notebook. Okay, and that will be very helpful to you in your examination. Okay, so now let us see how we can write the equation of motion of mass A. Let us see, this is your mass A, and you can see the force acting on this mass is T1 due to the first spring, and another force acting on this is T3 due to the third spring. Okay, and if you will resolve these forces into its components, you can see this figure. Since this angle is alpha 1, so if you draw a horizontal line from here, this angle will be also alpha 1 from geometry. And so the component in downward direction will be what? The component of this T1, as this angle will be alpha 1, so component of T1 in downward direction will be T1 sine alpha 1. Its another component will be T1 cos alpha 1 in horizontal direction, but I am not showing that. Now again you can see the force acting on this A, another force is T3, and this angle we have considered, this is alpha 3. So the component of this T3 in upward direction, that is in positive y direction, this will be T3 sine alpha 3. Okay, and another component will be in this direction, this is T3 cos alpha 3. But in horizontal direction, the component of T1 and T3 will cancel. And if your aim is now to find what is the net force acting on this in downward direction, you can see as the restoring force is always written with negative sign, because it tends to decrease the displacement, it opposes the acceleration, and so the net force acting in this downward direction will be equal to what? This will be T1 sine alpha 1 minus T3 sine alpha 3. Okay, this is the net force acting on mass A in downward direction. But if this force acts as a restoring force, then while writing the equation of motion, you have to put here minus sign. This minus sign, you know, it is put it before the restoring force to imply that this force always tends to bring the mass at its equilibrium position, or it always opposes the displacement. So we have to put minus sign, and when you will put minus sign before it, the restoring force acting on this mass will be what? This will be minus T sine alpha 1 plus T3 sine alpha 3. Okay. Now in the similar manner, you can again find the restoring force acting on the second mass B. And for this you can see this figure that the two forces acting on this B are what? These are the tensions T2 and T3. Okay, see this figure. Again, this angle I have considered this is alpha 2. So this angle above this line will be also alpha 2. This angle is alpha 3. So this angle made with horizontal by this T3 line will be also alpha 3. So now let us try to find the restoring force acting on this mass B. Okay, let us try. You can see this is mass B. Okay, and the forces acting on it are T2 and T3. Okay, and this angle you have seen is equal to alpha 3 and this angle is alpha 2. Okay, so component of T2 in downward direction, that is in negative y direction, will be what? This will be T2 sine alpha 2. Okay, and the component of T3 in downward direction will be T3 sine alpha 3. So this is the net force acting in downward direction on mass B, and this will be the restoring force. Again, due to the restoring nature, when we will write the equation of motion, we have to put minus sign here, and reason you know, because this force always tends to decrease the displacement. Okay, so you can see the restoring force acting on mass B, if we denote it by F2, that will be equal to minus T2 sine alpha 2 minus T3 sine alpha 3. Okay, so in this way, by these free body diagrams, we have obtained the restoring forces acting on the two masses. Okay, now after getting the values of restoring forces acting on mass A and mass B, that is on moving part of our system, now we can easily find the equations of motion of the two moving parts by applying the Newton's second law of motion. You know, this restoring force will be simply equal to mass times acceleration of the moving part. So if you want to write down the equation of motion of mass A, what will be that? Mass of A is m and its acceleration at any moment t will be what? This will be d2 psi A by dt square, because psi A is its displacement at any moment t. And d2 psi A by dt square in dot symbol is written as psi A double dot. So equivalently you can write this is m times psi A double dot. Okay, and according to Newton's second law of motion, this m times psi A double dot, that is mass time acceleration, will be equal to the net force acting on our system in downward direction, and that will be equal to restoring force. And we have seen that this restoring force is F1 and F1 is this much. So we equate m psi A double dot equal to minus T1 sine alpha 1 plus T3 sine alpha 3. Okay, now again see this figure. You can see this angle is alpha 1 and this is just a right angle triangle because this angle is 90, and this displacement is psi A, and the length of the spring now is equal to L1. So from this figure you can easily say what will be this sine alpha 1. As you can see, this is equal to psi a, this angle is alpha 1 and this side is L1. So from this figure you can say that sine alpha 1 will be equal to psi a divided by L1. Okay, so in this equation you can replace this sine alpha 1 by psi a by L1. Okay, now see again that figure. What will be sine alpha 3? You can see here, this is your angle alpha 3. Okay, and the length of this third spring is now what? This is L3. Okay, and this BC you can see, since this displacement of mass B is psi B and that of A is psi A. So if you take this point as D, then BD will be psi B and CD will be equal to psi A. So this BC will be equal to psi B minus psi A. Okay, BC will be psi B minus psi A. You can see this is the situation. This angle is alpha 3, this length is L3, and this is psi B minus psi A. So sine alpha 3 will be equal to psi B minus psi A divided by alpha 3. Okay, so this is the equation of motion of the first moving part A of our system, and it reads like this: m times psi A double dot is equal to minus T1 times psi A divided by L1 plus T3 times psi B minus psi A divided by L3. Okay, now we will try to write down the equation of motion of the another mass B, and for this you have to see the forces acting on this B. As you can see, one force acting on B is T3, which is tension in the third spring. Another force is T2. Again, resolving this T3 and T2, we will find the restoring force acting on B in downward direction, that is in BD direction. And you can easily see from this free body diagram what will be that. You can easily find it. Let us first of all erase this, and then I will make the free body diagram, and then you can see how we can write the equation of motion. Let us see. One force acting on B is T3. This is your B. And another force acting on it is T2. And this angle is alpha 2. And this angle is alpha 3. You have seen that in that figure. So the component of T2 in downward direction. Okay, we are talking about the restoring force, so we have to think the component of T2 in downward direction, and that will be what? That will be T2 sine alpha 2. Okay, and we have already actually obtained this in the previous free body diagram, so there is no need again to repeat it, but let us see. And the component of T3, this will be T3 sine alpha 3. Okay, and due to the restoring nature, when we will write the equation of motion, we will put here minus sign. So equation of motion of mass B will be written as mass times acceleration of B, that is d2 psi B by dt square, which is written as m times psi B double dot, that will be equal to minus T2 sine alpha 2 minus T3 sine alpha 3. Okay, now again you can find the values of sine alpha 2 and sine alpha 3 from the free body diagram and then substitute it here. Again you can see this is in fact the situation. This angle is alpha 2, okay. This is your mass B and its displacement is psi B and length of this spring is L2. So from this figure you can see what will be sine alpha 2. This will be psi B divided by L2, okay. And again sine alpha 3 already I have obtained here. This is psi B minus psi A divided by L3. So instead of sine alpha 3 I have written here psi B minus psi A divided by L3, okay. So this is the equation of motion of the second mass B, okay. But we have already calculated the values of the tensions T1, T2 and T3 earlier in this equation 1. So now let us substitute the values of these tensions say in our equations of motion 2 and 3. So let us put the values of T1 and T3 from equation 1 in this equation 2. So now equation 2 will become m times psi A double dot equal to minus T1. But you have seen that T1 is equal to K times L1 minus L0. And so instead of T1 I have written here K times L1 minus L0 and times psi 1 divided by L1, okay, and plus T3, but T3 is K times L3 minus L0, okay, and times psi B minus psi A divided by L3, okay. Now let us divide this L1 minus L0 by this L1. So after divide and here by L3 to L3 minus L0. So after division you can write m times psi A double dot is equal to minus K times 1 minus L0 by L1 times psi A plus K times 1 minus L0 by L3 times psi B minus psi A, okay. In fact, in the similar manner, when you will substitute the value of T2 and T3 from that equation 1 in this equation 3, then you will get a similar result like this. This will be m times psi B double dot is equal to minus K times 1 minus L0 by L2 times psi B and minus K times 1 minus L0 by L3 times psi B minus psi A, okay. So these are the equations of motion of the two moving parts of our system, okay. Actually in this case there are the normal modes of oscillations are obtained under two approximations. The solving these equations 4 and 5 under two approximations we get the normal modes of oscillations or the frequencies of the normal modes of oscillations. And the two approximation under which we will find the normal modes of oscillations of this system are actually Slinky approximation and a small oscillation approximation, okay. So one by one separately we will discuss what will be the frequencies of the normal modes of oscillation of this system when we make our calculation under Slinky approximation and under a small oscillation approximation. So let us see first of all what will be the normal modes of frequencies in case of Slinky approximation. Actually when you say Slinky approximation, what does it mean? Actually in this approximation the natural length L0 of the spring is much smaller than its extended length. So as L0 is the natural length and L is the extended length, so in case of Slinky approximation we have to take L naught much smaller than L. L naught much smaller than L. So if we now talk about this term, as our equation contains L naught by L1, L naught by L3, L naught by L2, what will be now these terms? You can see this L naught by L1. This can be written as L naught by L times L by L1. Actually, here this L naught by L1 has been expressed as a product of two terms. So this is actually second order smallness, and so can be neglected with respect to 1. Okay, because L naught is much smaller than L1. Okay, so in Slinky approximation, we will simply neglect L naught by L1 in comparison to 1, L naught by L3 also in comparison to 1, and this L naught by L2 will be also neglected with respect to 1. So making this approximation, or you can say that neglecting all the terms L naught by L in comparison to 1, now our equation of motion defined in 4 and 5 will become what? You can see when this approximation will be applied, now then equation 4 and 5 will become simply like this: m times psi a double dot equal to minus k times psi a. Because here we have neglected it, so this is minus k times psi a, and this will be plus k times psi b minus psi a. So m times psi a double dot, this is minus k times psi a plus k times psi b minus psi a. Okay, and similarly the second equation will become m times psi b double dot equal to minus k times psi b and minus k times psi b minus psi a. After getting these results, can you remember your previous lecture on the longitudinal mode of vibration or oscillation? When actually in my previous lecture I have discussed the modes of vibration in case of longitudinal oscillation, then you have seen, you can remember, these were the equations of motion. So these equations are simply the equations of motion of this coupled system in case of a small longitudinal oscillation. Okay, and you have already discussed in your previous lecture what are the frequencies of the normal modes of vibration in case of normal oscillations. Can you remember? There were two modes of vibration. First one was omega, the frequency for the first mode of vibration or oscillation was omega 1, and that was given by a square root of k by m. The frequency of the second mode was omega 2, and that was a square root of 3k by m. Can you remember? Already we have discussed this result. Since the equation of motion, even in this case of transverse vibration but in Slinky approximation, becomes identical as that in case of the equation of motion in case of the longitudinal oscillation. So you can say that the frequencies of the two modes of vibration will also remain same, and shape or configuration of the system will be also same. As we have already derived these results, so here I will write directly. So you can say that hence the two normal mode frequencies will be what? The first one, omega 1, will be equal to a square root of k by m, and another is a square root of 3k by m. And you have seen in the previous lecture that in this case the shape of the two modes, that is shape of the first mode, is given by psi b divided by psi a in first mode. You have seen earlier that this is equal to plus 1. So you can say that in first mode psi b is equal to psi a. Okay, and in the second mode you have seen earlier, I have here written it directly, that psi b by psi a in second mode is equal to -1. So the first mode is called in phase mode, and you know the second mode is called out of phase mode. Okay, because in this case there will be a phase difference of 180 degree between the two moving parts. So when one mass A will move up, mass B will move down. But in the first mode, when mass A passes through the equilibrium position, at the same time the another mass also passes through the equilibrium position and in same direction. Okay. So you can say that in Slinky approximation, the frequencies of normal modes of transverse vibration are the same as those of the longitudinal oscillations. Okay. I think the calculation is very easy, very interesting, and you are getting the things easily. Okay. Yes or no? Definitely we have to say yes, because this is not a very tedious concept. You can take it, you can get it very easily. Now we will talk about the another approximation under which we will discuss the normal modes frequencies, and this is actually the small oscillation approximation. When you talk about a small oscillation, you know, in case of a small oscillation, the displacement of the moving part of our system from its equilibrium position is very small. It means the oscillation takes place near about in the hitherto of the equilibrium position. Okay. So you can say that in this approximation, oscillating parts of the system stay close to the equilibrium position. And as the system remains very close to the equilibrium position, so the length of the springs during its oscillation or when the system is displaced will be not very different from its length in the state of equilibrium. So you can take that length of the three springs L1, L2, L3 in this condition will be almost equal to L, which is length of the spring in equilibrium state. Okay. So if now you have to write down the equation of motion of this system in this small oscillation approximation, you have to replace all these L1, L2 and L3 by L. So you can see these are our original equations of motions which we have defined in equation 4 and 5. And if you now write these equations in case of a small oscillation approximation, what you have to do? This L1, this L3, this L2, all these will be replaced by L. So replacing these by L, you can see our equations of motion will become like this. This is m times psi a double dot is equal to, sorry, the page has been turned, but this will be just okay. Don't worry. See here. Okay. So this first equation, this will be minus k times 1 minus L naught by L. See here, L plus k times 1 minus L naught by L times psi b minus psi. Now if we consider that this k times 1 minus L naught by L, this is equal to k star. If we assume, then this k star is actually called effective value of a spring constant in this condition. Okay. So now write k star instead of this k times 1 minus L naught by L. So this equation will be now m times psi a double dot equal to k star psi a plus k star psi b minus psi. Okay. And the second equation, you know, this is m times psi b double dot equal to minus k times 1 minus L naught by L2, but L2 is now replaced by L times psi b, and minus 1 minus L naught by again L instead of L3 times psi b minus psi. Again we will write K star instead of this K into 1 minus L naught by L. So the second equation of motion becomes m times psi b double dot equal to minus K star psi b minus K star psi b minus psi. Okay. Now again see this equation 6 and 7 and compare these two equations with the equations which we have obtained earlier in the previous lecture in case of normal modes of longitudinal vibration of the coupled massage system. You know, in that condition, these are our equations of motion. So comparing the equations obtained in equations 6 and 7, you can see these equations 6 and 7 are completely identical to these equations of motion in case of longitudinal oscillation. The only difference is what? Only difference is the K in this equation has been replaced by K star. So you can say that these equations are same as that the equation of motion in case of longitudinal oscillation if K is replaced by its effective value K star, which is equal to K into 1 minus L naught by L. Okay. So we can find now the frequencies of the normal modes of vibration, because you know in case of longitudinal oscillation the frequencies of normal modes of vibration are what? The frequency of vibration for first mode is omega 1 equal to a square root of K by M, and that of the second mode omega 2 is a square root of 3K by M. So if now you want to find the normal mode frequencies in case of transverse vibration, but in under the condition of a small oscillation approximation, what we will do? Only you have seen that K will be replaced by its effective value K star, because the only difference between these equations of motions and the equations of motion defined in 6 and 7 is what? The only difference is that K star has been written at the place of K. So if your aim is now to find the two normal mode frequencies in case of transverse oscillation of the coupled masses under the small oscillation approximation, we will have omega 1 equal to a square root of K star by M. But you know K star is equal to what? This is K times 1 minus L naught by L. So the frequency of the first normal mode of oscillation, this will be a square root of K by M times 1 minus L naught by L. And omega 2, which is actually a square root of 3K by M, that will be written in this case 3K star by M. Okay, and it's a square root. Again, substituting the value of K star, you can see that omega 2 will be equal to a square root of 3K by M times 1 minus L naught by L. So these are the frequencies of normal modes, or you can say the normal mode frequencies under the small oscillation approximation. Again, the shape or configuration of the two modes are same as in case of longitudinal vibration, and these are given as psi b divided by psi a in case of mode 1. This equal to plus 1, that is psi b is equal to psi a. Okay, and in mode 2 the shape or configuration is given by psi b divided by psi a, and this is equal to minus 1, so psi b is equal to minus psi. Okay, now you can see In case of longitudinal small oscillations, the two normal mode frequencies are what? First one, omega 1 is equal to root over k by m, and the another omega 2 is root over 3k by m. But in case of the transverse oscillation, particularly in a small oscillation approximation, these frequencies are omega 1 equal to square root of k by m times 1 minus L naught by L, and omega 2 is 3k by m 1 minus L naught by L. Okay, so in this case, if your aim is to write this omega 1 in case of transverse vibration, that will be what? That will be, if you write it as omega 1 prime, let us denote this frequency omega and omega 2 now as omega 1 prime and omega 2 prime. Then what will be this? This will be omega 1 times root over 1 minus L naught by L. You can see, instead of root over k by m, we will write omega 1. And similarly, omega 2 prime, this will be written as omega 2 times 1 minus L naught by L. Can you say that between omega 1 prime and omega 1, which is greater? Definitely you can say that this omega 1 is greater, because a square root of 1 minus L naught by L is a number smaller than 1. And when you will multiply any quantity by a number which is less than 1, the value is decreased. So you can easily say that this result shows that omega 1 prime is less than omega 1. And this result implies that omega 2 prime is less than omega 2. So I have written it here. You can see that comparing equations 8 and 9 with the above results, we find that the mode frequencies of the transverse oscillations, that is omega 1 prime and omega 2 prime, are smaller than their corresponding frequencies of the longitudinal small oscillations. Okay, so in this way we have completely discussed the concept of normal modes of oscillation of a system of two coupled masses in case of transverse oscillation and in case of longitudinal oscillation. Actually, in the previous lecture we have discussed the case of longitudinal oscillation, and in the present lecture we have discussed the concept of transverse oscillation. And after these two lectures, the complete concept of the oscillation of two coupled masses is now completed, and I hope you have now a clear picture of this problem in your mind. Okay, thank you very much.